Okay. So, welcome to the last pre-midterm 1 lecture. Let me remind everybody again that next Tuesday we do not have a regular lecture because we have an exam in the evening. That lecture will be we'll have a review session instead, which will not be in this room, but I believe in 217 Noise. There is a conflict exam being planned for the afternoon after the regular exam. If you want to or need to take the conflict exam, please register by the end of the day tomorrow so that I know who's coming. I will announce the rooms that the exam. There are 3 different rooms. I'll announce the rooms, and you'll distribute by the third letter in your middle name or something. But we'll announce all that on the website over the weekend. Are there any questions about administrative, not content questions about the upcoming exam? Okay. A lot of you have been coming to office hours with old exams, asking, how would I do this? How would I do that? That's perfect. Keep doing that. Keep doing that tomorrow. Keep doing that on Monday. Bring those old exams to the review session on Tuesday. Those are exactly the kinds of questions we'll be asking, but those are not exactly the questions we're going to be asking.
Actually, where are the old exams? Where can you find it?
The old exams are, you Google for my name and algorithms, or you go to the website algorithms.wtf, which I own. Yes, WTF is a top-level domain. And this is where I keep the last sort of semi-official snapshot of the notes, although there have been some later revisions, and an absolutely complete archive of every homework problem and every exam that I've ever given. And for 374, all of the headbanging lab questions as well, in case you want more problems to play with. There are probably so many problems here that it's not really even useful to point you to this site, but at least it'll show you the kinds of problems that I ask. Okay? So, not yesterday, Tuesday, we started talking about hashing. And I spent most of the lecture discussing how to do chain hashing provably efficiently. So the idea behind a chain hash table is that you've got a primary array which you use your hash function to find an address in, and then every cell in this array is a pointer to some sort of secondary data structure, which in the most straightforward implementation is just a singly linked list, but in a more complicated implementation, might be another data structure, and in particular, it might be another hash table. And I described in particular this construction where if you let the secondary data structures be hash tables, but you adjust the size of the secondary structure to be the square of the number of items that hash to that particular address in the primary table, then you can guarantee just by doing this once that each of these tables with probability at least 1/2 there will be no collisions at all. And so maybe it'll take you a couple of tries to build this table. But then what you end up with is something where the access time is constant in the worst case. You look up the primary hash value, you follow a pointer, you look up the secondary hash value, and you're done. Question?
Yeah, so is it NI value that you estimate, or is the real
No, n sub I is the actual number
actual number?
that hashes into that. So if you were really going to implement this, you wouldn't aim for exactly n sub I. You would aim for some power of 2 that's close to n sub I squared, or maybe some power of 4 that's close to n sub I squared. And as you're building the structure, if you discover a collision, you just build the table twice as big and rehash everything. Okay. And then the analysis of collisions, you can show that assuming that your primary and secondary hash functions are universal, meaning the probability of a collision is 1 over the table size, then you won't get any collisions here with some reasonable probability, and the total size of this structure is only going to be order n in expectation. Yes?
What do we do that so much for?
I want to make the table big enough that the probability of there being any collisions at all in the table is less than 1.
What's
N sub I is the number of things that hash into slot I in the primary table. It's the number of things that I want to put into the secondary data structure. Okay, so N sub I is the primary hash function, the number of things that hash to value I. Okay, so assuming that I have universal hashing, and if you remember, universal means the probability that any 2 items collide is at most 1 over m, and in fact, I can substitute any constant here that I like. This gives you constant worst case access time, linear expected space. If you want a stronger guarantee on the space, say I want to make sure that the space is order n with high probability, not just order n in expectation, you need to make a slightly stronger assumption about how good your hash functions are, which I haven't shown you how to actually enforce yet, but we'll see that by the end of the lecture today. Okay? What I want to talk about today is the other way of dealing with collisions, which is called open addressing. And the idea behind open addressing is I want the data structure to be an array, full stop. Okay? The idea is that, here's my hash table. There might be some cells in the table that are occupied by other data that I don't care about, not just the value x that I'm looking for. And when I'm looking for x, I am going to probe some sequence of hash values until either I find x or I find a cell in the table that's empty, at which point I will give up and say x is not in the table. Okay, so look up x is going to be something like following. For I gets 1 to infinity, if the table at the ith hash value of x contains x, I return true. Else, if the table at the ith hash value of x is some null value, then I'll return false. And the idea is that this sequence of so-called probe sequence probe sequence for x, each of these probes is defined by some hash function. And this is a good probe sequence if it actually explores the entire table, which means I don't actually have to go to infinity. I can just sort of imagine without loss of generality, once I've explored n different spots or m different spots in the table, actually I can really do it with n. Once I've explored some finite number of slots in the table, I know I've actually searched through the entire table, and at that point I can just give up. Okay. Now, what I don't want to do, however, is, you can think of this as sort of some ideal pie in the sky. How would you generate these probe sequence for each of these, each element? And so, sort of the ideal case is that for all x, this probe sequence h1 of x, h2 of x, and so on, is move that down to the next page, is a permutation of the possible hash values, and moreover, it's a random permutation of the hash values, meaning uniformly generated, chosen from all of the m factorial permutations of those addresses. So a sort of strawman model for how open address hashing might work is, for every element x, I imagine a random permutation of the indices in the hash table. And when I want to look up x, I will probe the hash table in order determined by that random permutation until I either find x or I find an empty slot. If I'm inserting x into the hash table, I will probe using that probe sequence until I find an empty spot, and I'll put x there, or until I find x and I'll say it's already there.
Why is this randomness needed here?
Well, for the same reason that randomness is needed in general. The idea is that if you have too much correlation between the various kinds of probes, then you can imagine, in principle, you might open yourself up to some kinds of timing attacks.
Oh, so that actually it's not random.
I mean, it's the same. I mean, even if you only have one hash function and if you get a collision, you just give up. If that hash function isn't random, your data structure is not going to work in an adversarial setting.
Yeah, of course, but the permutation is random. It seems kind of not that directly.
Well, I mean, this is an extremely strong and wholly unrealistic assumption. But if I want to think about open addressing hash tables in the abstract, and I want to do sort of a back of the envelope, how is this going to work? Let's start with the strong, an extremely strong assumption and see how it's going to go. Under this assumption, the expected time for a search for any particular item, well, let me just write it out in English instead of trying to use notation. The expected time for a search is on the order of how do I want to write this? So as the table gets more and more full, the time to do the searches gets longer and longer. And you can essentially think of the time to do a search as a kind of coupon collector problem similar to the random permutation problem in the homework, where the second algorithm that we gave you in part B of that question was, okay, for the next item, I'm going to randomly probe my table until I find an empty spot. If an alpha fraction of the table is empty, I'm going to need to do 1 over alpha probes before I actually find something that's empty. So a similar thing here, if I imagine that I have n items stored in a table of that has m n slots, then I'm going to have m minus m minus m empty slots, and so the probability that a given random slot is empty is going to be m minus n over m, which is 1 minus n over m. And so the expected number of probes before I find an empty spot is going to be the reciprocal of that, and m over m minus m. Okay. And again, this is exactly the same analysis that went into the homework. Pardon me, we're not ready for that picture yet. Okay. So again, this fraction n over m, which we saw in the analysis of chain hashing, shows up again as a parameter in the analysis of the running time. Only now, because I cannot have the table be, I cannot have more items in the array than I have spots in the array, that fraction is always less than 1. Yes?
So when you want to build a table, you fix these.
Okay, so what I want to imagine when I'm talking about this as a first cut is all of the parameters are fixed. Now, in fact, the hash functions are going to be determined by some small number of random numbers, the salt parameters, just as they were for chaining. In practice, when you're building these things, when you discover that something has gone wrong, either the table is too full, or you're deleting things and the table is too empty, or you get more collisions than you expect, what you do is you generate a new set of salts, a new hash function, and you rebuild the table, possibly bigger, possibly smaller, to try to adjust for whatever failure mode you have. And it turns out that doing these adjustments on the fly doesn't add anything to the overall running time of the data. It's exactly as if the data structure were the size that you needed from the beginning, up to some very small constant factors, which you can actually make arbitrarily small just by tuning when you trigger a rebuild. Okay? So if you were really implementing these things, no, these parameters are not fixed. You can adjust them on the fly. But for purposes of analysis, it's enough to consider we know the right values for the parameters, and we'll just go from there. Okay. So a table that's 3/4 full, you're going to get, you're going to need roughly 4 probes. A table that's 9/10 full, you're going to need roughly 10 probes. So in general, when we're talking about open address hash tables, we like this fraction to be some small, but not too small constant. Aim for something like half or a third. Okay, I want roughly half or roughly a third of the cells in the table to be empty. In fact, more than that empty cells, then I'm wasting space. fewer than that empty cells, then the time is going to be bigger. Okay. Now, in practice, not possible. You really can't do this because it would require, just like the ideal random hash functions when you're doing chaining, it would require actually storing the permutation attached to X in some table somewhere, and now you're just making a more complicated hash table so that you can use your hash table. So in practice, what you need is a relatively simple heuristic for generating this sequence of probes. And it turns out that the very first heuristic that anyone ever came up with back in the mid-1950s actually works, which is somewhat surprising. People have come up with all sorts of things that are much more complicated and seem to have more interesting theoretical properties, but in practice, keeping it simple actually works best. And this is called linear probing. And the idea behind linear probing is you look in the spot that's given to you by your hash function. If that's occupied with the wrong thing, you just go to the next spot. And you just continue scanning forward until you either find an empty spot or you find the data you're looking for. If you've hit the end of the array, you just start over at the beginning. So the ith hash function of X is just some fixed single hash function of X plus I mod the table size. Okay. This really works much better. I mean, there are other more complicated ways of generating the probe sequence. So there's something called quadratic probing, where you have an I squared here instead of an I. And the idea is that if you're taking small steps and not finding any gaps, maybe you should start taking bigger steps to jump over the clump of stuff that you're searching through. There's another one called double hashing, where you have two hash functions, h and h prime, and you take h of x plus I times h prime of x. So the first hash function tells you where you start, and the second hash function tells you your stride through the table. And so again, the motivation that people give for for spreading out the data in the hash table is that if things clump together, then it's more likely that this probe sequence is going to be long before once you have a sizable clump in your table, if you're building it with linear probing, you're more likely to land in the clump, and then the clump is going to get bigger. Okay? So there's some unfortunate and somewhat unintuitive clumping here. If the load factor gets too close to 1, and people spent a lot of energy in the 1970s and the 1980s coming up with these more complicated strategies to spread the data out in the hash table. In practice, this is actually counterproductive. Okay? So it is true that when you look at a hash table that's built by linear probing, the data tends to clump together into a small number of contiguous regions rather than being uniformly spread out through the data. But that is actually good. Why is that actually good?
Memory reading?
So both of you said it, but using different words. You have better cache behavior. Remember, in modern computer system, when you access a single element in an array, you don't actually just pull that one element out of RAM. You pull an entire block of elements out of RAM. And then later accesses to the same block are cheaper because it's close. That memory is closer to the CPU. In fact, this happens at multiple levels of resolution. So if you actually do the experiments on a modern CPU, it turns out that this clumping, it actually helps you because it cuts down on the cache performance. Whereas if you take longer strides through the hash table, you're much more likely to get cache misses. And doing 5 times as many probes with no cache misses is actually much better in practice than having 5 times fewer probes but twice as many cache misses. Yeah.
I don't understand. So go back to the ideal case. So
Yeah.
you have this set of hash table, hash functions, right?
Right.
You said this is unrealistic, but I don't understand. For example, you have hash functions in the set, and then all you need to do is just to probe one of them. Like if this doesn't work, then the next one, and then which case is 5? It's still constant. Why not?
Okay, so I could in principle have an array of size n, where in each element in that array, I store the salt for a particular hash function. And then when I'm doing hashing, I could walk down this probe sequence. The problem is that's going to give me a sequence of samples with replacement, not a random permutation, which is a sequence of samples without replacement. Now, the distinction between sampling with replacement and sampling without replacement actually turns out to be pretty minor. So with that kind of construction, you could actually do this, but then because you're generating these sequences using a small number of salt parameters, there's some independence between the different hash functions, which gives you different statistical behavior than if you're really doing things with ideal randomness. Okay? So it turns out not to work. Right? I mean, you can make it do something, but it won't be as good as what you get with linear probing. Okay, so I'm not going to describe exactly the analysis of linear probing. What I'm going to do instead is describe a surprisingly more modern heuristic for open address hashing, which actually has slightly better cache behavior than linear probing, and is, if anything, easier to implement than linear probing. And if you were actually going to do an open address hash table, this is the probing strategy that I would recommend that you do. This is called binary probing. And the idea is, first of all, I'm going to assume that the hash table size is a power of 2, and moreover, because I want to align it nicely with the memory hierarchy, it's helpful to assume that the table is actually aligned in an address, which is a multiple of the size. And now my ith probe is going to go to the address given by this. The normal hash value, which is an L-bit integer, exclusive OR, with the probe number, which is, again, an L-bit integer. Like, this is just bitwise exclusive OR. Right? In C, this would just be a caret. Okay? That's the probe sequence. And the reason why why this has slightly better cache behavior is, if I imagine now, didn't quite get a power of 2 here, so there's a power of 2. Let me suppose that this is h of x. What's going to happen is I'm going to explore addresses. First of all, I'm going to explore the address at h of x. That's where I'm going to start. So I'll start here. And then I'll flip the low order bit. And then I'll consider all addresses where I'm different from h of x in the second to low order bit. That's these two. And then addresses where the third least significant bit differs. That's these 4. And then where the fourth least significant bit differs. That's these 8. And so on. So the order in which the table is explored is fill up the current block of size 2 to the whatever, explore it in some order, and then move on to the neighbor block of size 2 to the whatever, in just the right order that you end up exploring the entire block of size 2 to the whatever plus 1. And then you look at the sibling block of size 2 to the whatever plus 1, in just the right order to fill up the block of 2 to the whatever plus 2. And so wherever your lines are, your address boundaries are for cache lines or for pages, you're going to explore a complete cache line before you go to the next cache line. You're going to explore a complete page before you go to the next page. Okay. It also turns out that binary probing is easier, slightly easier to analyze than linear probing, which is, the best of all possible worlds. It's simpler, it's faster, and it's easier to understand. That said, it's not exactly easy to understand. Okay, it's easier than linear probing, slightly, but it's not easy. I'm going to give you a very, very high-level sketch of how to analyze this. But the punchline is that the expected running time of this probe strategy is constant if, first of all, n over m is smaller than, I think, half, and h is 5 independent. Or actually, I need 5 uniform. And what 5 uniform means is the probability that h of a equals I, and h of b equals j, and h of c equals k, and h of d equals l, and h of e equals l prime, because I don't want to use m, is at most 1 over m to the 5th. Now, I haven't showed you how to do hashing, any hash functions that have this level of independence. This is a much stronger assumption than just it's universal, which is what you'd get from this binary, you multiply by some random number and take the right window of bits. Right? I think actually, before I go on to the actual analysis of binary probing, let me show you how you would do this. How you would get a hash function that has more independence than just pairwise collisions don't happen very often. Okay. And to do this, I need to use an idea that dates back to the late 1960s, when people were starting to write programs to play games. So in particular, there was a researcher named Zobrist who was one of the pioneers in developing computer programs that played chess. And so Zobrist needed a hashing scheme to be able to say, okay, I've got my chessboard here. There's a black king here and a black queen here and a couple of black pawns, and there's a white knight and a white king, and here's a couple of white pawns and a white bishop. How am I actually going to represent this in memory? And what Zobrist did when he was developing this program is exactly the same kind of dynamic programming thing that you did in homework 2 with the Dr. River game. For every possible position in the game, Zobrist stored some information that indicates whether the program thought that white moving from here would win or black moving from here would win. And by chasing through the table, you could figure out what is white's preferred move if white goes first. And the way that Zobrist did this is he had a lookup table just filled with random numbers. And so, and he had a code that meant things like white bishop at c4. Okay, so this would be, I take my hash function for black king at, what is this? A, B, C, D, E, F, G, at G2, exclusive OR, and then there's some other lookup table. Actually, let me call this lookup table T. For white king at I forget. Does anyone play chess? Are the rows the letters or the columns the letters? The columns of the letters. Okay, so sorry. This is B7 and this is B1, exclusive OR and so on. And this table was just filled with random numbers. Okay, so this is Zobrist hashing. Now, if I wanted to go from the hash function for this particular position to, I want to move the king over one, what I would do is I'd take the hash value for this board, I'd exclusive OR with the king in its old position, which is just a single 8-bit integer code, and then I exclusive OR for the king at its new position. And so in constant time, Zobrist was able to transform the hash code for any position, any chess position you like, into any other position one move away. Because he's just taking all these random numbers corresponding to the way that you would describe the position in English. There's a king at this square, there's a king at that square. I'm just exclusive ORing them together. Okay? So this made Zobrist's chess programs really fast because he didn't have to hash the entire board every time he wanted to think about it.
Why is X Y working?
Because one reason is because I want to be able to do it fast. I don't want to have to worry about things like integer overflow, so I don't want to do add because I might add up a board full of lots of pieces and lose some significant bits, and then when I subtract off to remove the pieces of the board, I don't know whether that bit was there or not. In general, the idea is that if I take a random sequence of bits and I exclusive OR it with another random sequence of bits, the result looks like a random sequence of bits. In a much stronger sense than you would get just from adding. Yeah.
Is there a guarantee that there are no two bars that have the same value?
No, absolutely. This is pure engineering. There's absolutely no guarantees at all. Okay. I mean, I just told you the entire hashing algorithm. You build this table, which is big enough to store however many symbols these are, and you fill it with random numbers. Okay. So probably yes, there would be collisions, but in practice, they're rare enough that it doesn't affect you. Yeah.
Sorry, what's hash again?
I'm sorry?
What is hash?
H is this is the hash value for the old board. Right, so H is equal to the exclusive OR of the hash values, all the pieces, and then H prime is the hash value for the new position.
Okay.
Right? So this scheme was repurposed or reinvented by Carter and Wegman in the 1970s, as something called tabulation hashing. So again, I'm going to imagine that my universe is the set of all W-bit integers. All integers between 0 and 2 to the W minus 1 inclusive. And what I'm going to build is, so any item in my universe, I can write as a pair x comma y, where x is a 2 to the W, is a W over 2-bit integer, and y is also a 2 to the W over 2-bit integer. So pictorially, I have, here's x and y, and together these W bits make up the object that I want to hash. So in particular, if I'm hashing 32-bit integers, I might divide them into two 16-bit chunks. Okay? Now what I'm going to build is a table A and another table B that stores, it has each of the size of these tables is 2 to the W over 2. So for my if W is 32, each of these tables has size 65,536. And these are full of random integers. And I mean really ideal random, just for the, let's assume that somehow I have access to real random numbers. Okay. So I'm going to, in preprocessing, I'm going to fill these two tables up with random numbers. And I'm going to do this at the beginning of time when I create my hash function. And then my hash value for a given item, which remember is I think of as a pair of W over 2-bit numbers, is A, and I look it up X, and B, and I look up Y. And if necessary, I'll mod M. But remember, I'm also going to assume that M is a power of 2, so that mod is really just chopping off some lower order bits. Okay. So the idea is this is some random hash function for X. This is some random hash function for Y. And I exclusive OR them together. This is about as close to ideal random as you can imagine. Essentially what I'm doing is I'm expressing the universe as the product of two smaller universes, and I'm building ideal random hash functions on those two smaller universes and combining them. Okay? This simple idea, of course it can be generalized. So if W, 2 to the W over 2 is too big, I could instead divide my integers into smaller chunks. So, maybe if I'm hashing 64-bit things, I want to divide them into 8-bit things. And then my hash function for, an item is going to be now represented by a vector of length 8. This is going to be the exclusive OR from I equals 1 to 8, not infinity, but actually 8, of, table of random numbers for the ith table of random numbers, looking at position given by the ith digit of the item that I'm hashing. So, for example, IPv6 IP addresses, these are normally expressed as 16-bit integers. So I might hash them by creating 6 tables of size 64K, or 12 tables, each of size 256. And then I look up by using those as offsets into a table of random numbers and then exclusive ordering them all together.
Does increasing the size really affect the randomness or the independence?
No, what it doesn't. So increasing the number of tables does not actually give me more independence.
Does it decrease it?
It also does not give me less independence. What it does give me is a trade-off between the time that it takes me to compute the hash function and the space that I need to store the random number tables. So if I'm doing this on my cell phone, in particular, if I'm actually doing this on my cell phone, I don't have space for a 64K table of 32-bit random numbers. So I'm going to need to use more digits and more tables of random numbers, but those tables will be much smaller. And that means it's going to take me longer to actually compute the hash function.
It just seems to me that this table is decreasing by the factor of 2, but the number is increasing by +1. So the number of hashing is like just increased by +1, right?
Well, I mean, there is a trade-off here. And you can take it, in fact, all the way down to just having W tables, each of size 2. And you look up the individual bit And if it's a 0, you take this value, and if it's a 1, you take that. But then that's going to take log w time to look anything up. And you should think of w as some polynomial, 2 to the w as being at least some polynomial in n. So now you've got your your lookups are taking at least log n time. And now you've lost the advantages of hashing.
Yeah.
Okay. So the punchline here is, and this is not actually that difficult to prove. This is 3 uniform, but it's not 4 uniform. And it doesn't matter, again, how many different ways I split up the bits. So it's easiest to see in this case, again, I'm not going to go through the formalities here, but I want to give you some intuition why this is at least universal. If I have 2 keys x, y, and x prime, y prime, they're going to differ in, say, the first digit, and maybe the second digit will be the same, but then I'm taking this random value ax and exclusive ORing with this random value by. That's really not going to give me any information about some other random value ax prime exclusive ORed with by. And you can, walk through an argument that you don't gain any information, even if you know 2 hash values, you don't gain any information about a third. But it doesn't completely work because you don't get full independence. Because this is equal to 0. If I take my 2 favorite first digits, x and x prime, and my 2 favorite second digits, y and y prime, then the 4 keys, xy, x prime y, xy prime, and x prime y prime have hash values that are exclusive OR to 0. I mean, this just falls out of the definition of H. Which means if I know any 3 of them, I know the 4th. So it can't be 4-way independent. Okay. Nevertheless, there is a strong sense in which this is almost ideal random. And this is work by Mihai Petrashku and Mikkel Thorup in the mid-aughties. I think it was 05. What they showed is that even though you don't have independence, you can still show that the random events you would associate with these hash functions can satisfy weak versions of the Chernoff inequalities, which are, the Chernoff bounds are things where you assume complete independence of everything. And so what they showed is that you can actually still get Chernoff-style inequalities. It's just that some of the parameters in the bound on the right-hand side have some constant factors glued onto them and some additive error terms glued onto them. In other words, this is good enough for linear probing. And again, it doesn't matter whether you split into 2 pieces or 8 pieces. You get the same statistical guarantees either way. Right? On the other hand, that's not what I would recommend doing because the guarantees aren't quite as strong. There was still that almost in there. Here's another thing called modified tabulation hashing. And this was done by the same Thorup and one of his students, Zhang, in 2012. So this is really very recent. So you have a table that you look up by x, and then you have another table that you look up by y, and then you have another table that you look up by x plus y. And at this point, we're essentially doing magic. Penn and Teller up here saying, "Whoa, the hash function magically works." This is 5 uniform. And There's similar schemes if you need to break up your keys into larger numbers of chunks instead of just 2. So if I need to break things into 5 chunks, there's a similar formula that has, 9 terms. Moreover, if I want 7 uniformity, then, in general, I can get, if I want something that's k uniform with c chunks, then I only need about c times k table lookups. Using linear combinations of the various chunks as the indices into the tables of random numbers. What's really weird about this is that, yes, I really do mean addition there. I do not mean exclusive OR. If you do an exclusive OR there, it doesn't work.
X plus y.
X plus y. I mean, treat them as integers and add them. And in particular, x plus y has 1 more bit. And so table C has to be twice as big as tables A and B. Okay, so this is what I would recommend actually using if you wanted to do linear probing. Because now it's not just sort of close enough that it works. No, it works, the end. Okay. The proof of this fact is beyond the scope of this class. Yes? Right, that's exactly what it means.
And that would then say, give us a higher probability that it would work. Right?
Yeah, so the more independence you have, the stronger the claim about high probability correctness or high probability speed you can get. As I'll talk about later, there are other hashing schemes where you actually need higher levels of independence for them to be able to provably work. In fact, we don't even know what level of independence we need. That's an open problem. But nevertheless, you can adjust these schemes to work for those things. Again, there is a trade-off here. I mean, if I have to do C times K table lookups, that means that the running time of hash this value is order C times K. And so the more chunks I have to break things into to keep the table small, the longer it takes to compute a hash function. The more independence I need, the longer it takes to compute a hash function. But the running time here scales linearly in both of those quantities. If I want twice as much independence, I just need to take twice as much time.
This is not K and C, right? This is just 3.
Oh, right. I mean, this is, I'm hiding some low order term. It's like C minus 1 times K minus 2 plus 7. There's some complicated formula, I think. But it's order C times K where the leading constant is 1. Plus minus some low order terms. Okay. So let me see if I can give you some idea about why binary probing is fast. And this is really just going to, I'm not going to try to give details. This is really just intuition. If you want to see the details, they're in the notes. Let me try to give you a sense of what's going on. So, because I'm doing this exclusive OR with larger and larger integers, the way that the table is explored is first I'll look at x, then I'll look at the sibling of x, that's a block of size 2, then I'll look at the neighbor block of size 2, that gives me a block of size 4, I'll look at the neighbor block of size 4, and so on all the way up. So imagine for purposes of an analysis that I've defined this sort of recursive partition of the hash table into a binary tree of blocks. There's the big table all by itself, that's the root, and then it's split into a left side and a right side, and then 4 smaller ones, and then 8 smaller ones, and so on. So I'm going to write b sub k of x. This is the block of size 2 to the k containing the original probe h of x. And b prime sub k of x is the sibling of that block, which is the same as the block 1 bigger minus the block itself at size k. So the red blocks are these b sub k's, which I'll refer to as the ancestors of x. And these b prime sub k are the pink blocks, which I'll refer to as the uncles of x. Okay, so these are ancestors, and these are uncles. Because English does not have a gender-neutral term for sibling of ancestor. At least we're not speaking Chinese. Those of you who speak Chinese know this far better than I do, but English has maybe a dozen words that you glue together in various patterns to describe your relatives of various, grandparents of siblings of cousins of grandchildren. Chinese apparently has a unique name for every possible relation. Am I exaggerating? Anyone?
More than one unique name.
Oh, okay. Multiple unique names. Thank you. And I think it also depends on whether it's the grandchildren of your younger sister's husband or the grandchildren of your older sister's husband. There are distinctions like that. So we're going to go with uncles. So the way that you can think about how binary probing works is first I explore the actual location of x. Then I explore the 0th uncle of x, which is just the sibling of x. Then I explore the first uncle of x. Then I explore the second uncle of x. Then I explore the third uncle of x. And when I say explore, I may as well say, for purposes of analysis, that I'm going to, if I don't succeed at a particular level, I'm going to go up to the next level and I'm going to explore the entire block. I mean, the actual algorithm is faster than that. Okay? But again, just for purposes of analysis, I'm going to imagine that I explore the entire block. So that means that my binary probing algorithm looks something like this. I try looking at the original hash function. If I don't find anything, if I find either x or nothing, I return a Boolean. Otherwise, I say I haven't found anything yet. And then I walk through the uncle at level k in arbitrary order. Now, in fact, it's not arbitrary. It's a particular order. And I would stop early if I found something. But the first time I find something, I'll record a Boolean. And if I actually found something, I'll return it. Otherwise, I'll go to the next level. Now, I know that the entire table is not full. In fact, I need to assume that the table is at most half full for the analysis to work. And so I know eventually I will find an empty spot in the table, which means eventually this algorithm will halt. But the running time of the algorithm is going to look something like the following. The running time for a, well, let me just say, sorry, the expected running time. It's going to be at most, well, okay, there's a constant term at the beginning. Otherwise, it's the sum from k equals 1 to L minus 1, L being the size of the largest blocks, of order 2 to the L times the probability that the block at level, the uncle at level k is full. Full meaning it's got data in it. Every item is every slot in that block is occupied, but it's not occupied with x. And I'm imagining here an unsuccessful search. Eventually I'm going to discover an empty spot first. And so if I want to understand the expected running time of this algorithm, I need to understand what is the probability that a particular block of size 2 to the k in the table is full. And then I need to sum that up. Okay? So this is what we need to concentrate on, this probability. Okay. All right. So now let me go once again to the pattern of searches. And let me ask, for example, under what circumstances this particular block of size k, here that I just sort of stuck in the middle, under what circumstances can this block be full? Okay. So if a particular block of size k is full, one of two things can happen. One of those things is let's see. One is so-called popular. That means 2 to the k items hashed into this block directly. Now, not all of those 2 to the k items would necessarily be stored in that block because they're, well, is that true? Oh, no, it's not necessarily true because the block might have filled up before I got that many probes. But if I imagine just hashing 2 to the k things into this block of size k, if the first 2 to the k hash values are hashed into this block of size k, what would happen is this block of size k would be full and everything else would be empty. Because it would explore this entire block before I go anywhere else. Or the other possibility is that somebody overflowed into this block. That there was not enough room in some other block, and so the item that would have gone into that other block had to come here instead. And now the question is, what could overflow into this block of size k? And the answer turns out to be one of its uncles. Okay? In this particular case, the only for this particular probe sequence, the only uncle that actually could overflow into that blue block is this top level B5 of x. That's one of the uncles of the blue rectangle. Okay? So maybe my sibling was full, and so somebody tried to insert something into my sibling block and it overflowed into me. Or my first uncle was full and somebody tried to hash into that and it overflowed into me. Or my second one, or one of BK's uncles is full. Okay? But then, because I know that the very, very top block is not full, there's an induction argument that says, eventually, if one of my uncles is popular, then either that uncle is full or one of my uncle's uncles is popular. But my uncle's uncles are my uncles. So eventually I'm going to find a popular uncle. Okay? It's the kind that, always brought you the good Legos at Christmas. Right? In order to figure out what the probability is that a particular block is full, what this really boils down to is discovering whether a particular block. So what I need to know now is the probability that actually it turns out to be a particular uncle of x is popular. Right? What this means is I've got a block of size k, and 2 to the k things have hashed into it directly. Those are not necessarily all stored there because of overflows. It might be stored somewhere else. But now this is just not a statement about the contents of the hash function, but rather about the hash values of the objects that I'm storing in the table. The initial hash function, before I resolved any collisions at all. Okay? Now, if I start with this assumption now, say n equals m over 2, just because I need to nail down something about the load factor here. The expected number of items that hash into any block of size k is 2 to the k minus 1. And so what I'm asking for is the probability that this number of items that hash into this table is at least twice its expectation. Right? I expect, because the entire table is half full, that any particular block, on average, is going to be half full, assuming things are distributed uniformly. Okay? And so, in order for something to be popular, it had to get twice as many things as it should have gotten in expectation. So, this is I need a tail inequality here.
Is that equals or greater than?
Well, it can't actually be greater than. So the tail inequalities are all phrased in terms. No, I'm sorry. It can actually be greater than. It's possible. There's a small chance that everything will hash to the value 0.
Oh, yes.
Right. Okay. So at this point, I start doing math, which I'm not going to show you. Okay. But because everything is 5 independent, then I can apply the fourth moment inequality. Why do I lose a level of independence? Because everything here that I'm talking about is a block that's determined by a particular search key x. So this particular search key x and any 4 other things are independent. But once I've nailed down that x, I only have essentially 4 degrees of freedom left. Okay? And what the fourth moment inequality says is that this probability of being popular is at most 1 over the square of the size of the block. So it's order 4 to the minus k. If I tried to use Chebyshev's inequality here, I would only get 2 to the minus k. By using the fourth moment inequality, I get 4 to the minus k. And now, if I go back to my, so if I go back and actually do the math from the beginning, what I end up with is something like the expected time is equal to the sum over all values of k of order 2 to the k times the probability that some particular block of size k is popular, which is order 2 to the k times order 4 to the minus k, which is a descending geometric series, which is order 1. If I try to just use Chebyshev's inequality, where I only need pairwise independence, I get a 2 to the minus k here, which means I'd end up with log n here. All right, so I need things to be independent enough, otherwise I can't guarantee the constant expected running time. Okay? So that's as much as I want to say about binary probing. The analysis of linear probing is almost exactly the same. The last thing I want to leave you with, and I know that I only have 5 minutes, and I know that it's dangerous to say, I have only 5 minutes, let me show you one more thing. I want to show you one more. I'm not going to show you the analysis. I'm not going to state any theorems. I'm just going to show you the high-level strategy and say, it works. This is called cuckoo hashing. Cuckoos are not just clocks. Do you even know what they are? They're birds, but what do? Yeah, they go into other birds' nests, and they push the eggs out, and then they pretend to be that bird's babies, and that birds are stupid, so they feed them, right? So the idea is that I'm going to imagine now that I have a table, and I'm going to store x at either the table at its hash value or indexed at the other hash value. So I have two hash functions. When I want to look something up, I say, is it here or is it here? The end. Okay? Now, what happens if I have some data stored in the table already, and I decide I want to insert a new item? I want to insert f into the table. So I look at the two places that hashes in the table, and if one of them is empty, I just put it there. Okay, no big deal. But what happens now if I decide I want to insert g, and both of the slots in the table are occupied? What do? I push one of them out. I say, well, too bad, you lose. G is going to go here, and now B is out of the table. And of course, B is pointing back, looking sadly back at the cell that it just came out of, but it has somewhere else that it could go. And so, okay, fine, I'm going to push D out of the table, and D is fondly looking back where it could be, and it points to somewhere else. Sorry, that would have been B. And somewhere else to go, I put it in that other place. And this turns out, if the table is at most, I think, 25% full, this process converges in constant time in expectation. With high probability, it converges in log n time. But this is only for insertions. The search is, it's either here or it's here. The end. Yeah?
So it's like the cache strategy where the algorithm is recently.
Yeah, it's very much like an LRU paging strategy, except I don't actually keep track. How do you choose which thing to kick out? Doesn't matter. Do it however you like. In practice, you would flip a coin, but it doesn't really matter which one you do. So I'm not keeping track of which hash value has been accessed the most recently. I just say, you're in my way, get out. And say, okay, I'll go to my other house. Right? And it is possible that this will get into an infinite loop, but the chances of that happening are vanishingly small. And if it does happen, you just rebuild the table. And if you want to actually make this work, use tabulation hashing. And this is what the internet backbone uses. We're done. With a minute to spare. Okay, thank you.
So where did the factor 2 to the k come from? The whole thing.
Basically, if the block is full, then I will explore the next uncle completely.
Also, just because the k is the k uncle of the block.
Yeah.
Okay.
Yeah. So it's just, if it's popular, one way to think of it is if that block is popular, I'm just going to explore the whole thing.
And one thing about Silver's hashing, like, what does he actually store in like?
What does Zobrist actually store?
Yeah.
So the idea is, there's a recurrence that says, well, if it's white's turn, I want to try all possible things, and I'll take whichever move is the best for white.
Okay.
And so what it will actually store is either what the best move is, or what the value is if you make the best move.
I see, and the way he does that is he keeps like hashing to the old.
Right. So I mean, he's really doing a standard backtracking search, except he's memoizing it using hash table.
Yeah. But okay. That makes sense.
And then at some level, you get deep enough that I don't want to keep recursing, and then you use some heuristics that say that looks like a pretty good position for white.
And last question. I didn't fully understand, like, when we talked about yesterday, we